Okay, so in chapter 4, we'll study 2D and 3D motion. Okay, essentially. So in the previous chapter we studied motion in 1 dimension, and so now we are going to study a more realistic motion, a motion in 3 dimensions, and then we'll specialize to everything we learn. We'll specialize to 2D motion. The reason we want to study that particular 2D motion is the following. We'll study projectile motion, which is, let's say you toss this object. When it's traveling under the influence of gravity, that thing is traveling in a single plane. That's traveling in 2 dimensions. Okay, so that's what we're going to study. So when you toss an object, and you will learn that the trajectory of an object that is traveling only under the influence of gravity, what does that statement mean? It's traveling only under the influence of gravity. Air resistance is negligible. Okay. So this trajectory is a parabola. This is a 2D trajectory. So we'll study 3D motion and then specialize to that. This is 2D motion and the trajectory is a parabola. Yeah. All right, so we are studying motion in 3 dimensions. Okay. And again, we've been saying this ad nauseum. When somebody asks you to describe a motion, what are they asking you? And there you go, my friend. So for instance, if you're in a plane and this is your flight path, and somebody asks you to describe this motion, what they're asking you is for these 3 functions. Your x, y, and z coordinate as a function of time. Okay? So we'll do an example. Okay, so what I wrote here is a spiral motion. It's a motion where you're spiraling upwards, and the z-axis, along the z-axis, what you're doing is you're accelerating at a constant rate. Okay, so this is if you could come up with a joyride like this would be, and you could make a lot of money. Okay, so, but anyway, so that's, okay. So here's a motion again. And you already have learned that if somebody describes this motion, you can calculate everything there is you want to calculate it from this function. Okay, so for instance, if you were interested in the velocity, what was velocity at any given time?
The derivative of the position.
That's right. It was dr by dt. Okay, so it would be d by dt of this function times I, d by dt of this function times j, and d by dt of that function times k. Okay, what is that? What is the derivative of cosine t?
Negative sine.
Very good. What is the derivative of sine?
Cosine.
And 2t. So acceleration. No, so acceleration is not just acceleration in the z direction. The acceleration in the z direction is constant, but so you have centripetal acceleration and acceleration in the z direction. Okay. So again, given this description of motion, you're able to calculate velocity and acceleration. Okay. So again, so if somebody asks you to describe this motion, what they're asking you is to give these three functions, x, y, and z, okay? The displacement vector is a vector pointing from your initial point to the final point, okay? So let's say if you were here now and if you're there later, so this is your initial position, there is your final position, the displacement vector is that vector, okay? And so this is R2 at time t2, so if you want, you can write this like this, R at time t2 minus R at time t1, okay? And that's the shorthand notation for this, okay? R at time t2 is written as R2, and R at time t1 is that, okay? So there's the displacement vector. And that's equal to that. The difference in x coordinates, my I, plus difference in y coordinates, j, and so on. You guys understanding this? All right. So if you calculate the average velocity again, we will be interested. See, this is instantaneous velocity. What is the velocity at this instant? But if you wanted to calculate the average velocity between now and, let's say, next 10 seconds, then so the average velocity between two instants, the average velocity is the displacement vector divided by the time, okay? And you see this is a vector, which is that, divided by time would be a velocity in this direction. So the average velocity points in the same direction as the displacement vector. The instantaneous velocity is in the limit delta t going to 0. So as delta t goes to 0, this thing gets closer and closer to that point, and the instantaneous velocity is tangent to the curve. Okay? So if for this motion, if that were the curve, this guy is tangent to the curve. Yep. All right, so that's a vector that's tangent to the curve. Okay, so there's the average velocity. Again, we won't be calculating average velocity too often. So the instantaneous velocity is in the limit delta t going to 0, which is dr by dt. Okay, so dr by dt is dx by dt. This is called the x component of the velocity. dy by dt is the y component of the velocity. dz by dt is the z component of the velocity. Okay, so again, here is a trajectory, a three-dimensional trajectory. The instantaneous velocity is tangent to the curve. Okay. All right, I can't open the link. Okay. Acceleration. When do you accelerate? Whenever velocity changes. Okay. So acceleration is change in velocity divided by the time over which that change happens. Okay, so if your velocity was not changing, this would be 0. Your acceleration would be 0. Okay. So again, change in velocity is velocity at time 2 minus velocity at time 1 divided by that. Okay. So in this case, let's say that the blue line is your trajectory. There's your velocity. Velocity is tangent to the curve, so there's the velocity at the initial instance. There's your final velocity, and the difference of the two is this guy. So there's your final velocity. There's your initial velocity, and the difference in two. There's the change in velocity. So which way is the acceleration pointing? The average acceleration.
Acceleration?
Hmm?
Same as acceleration?
No, which way is it pointing in this case? It's pointing in this direction. Okay, see, it's the change in velocity divided by that. Okay, so it's pointing in this direction. So, all right, so it's somewhere like that. Okay. So anyway, this is the definition for average acceleration. Okay. What this is instantaneous acceleration. Okay. All right, so again, we won't calculate average accelerations too many times. Okay, so here's the average acceleration, and in the limit delta t going to 0, that's the instantaneous acceleration, and that's dv by dt. So dvx by dt is the x component of the acceleration, dvy by dt is the y component of the acceleration, dvz by dt is the z component of the acceleration. Okay. So acceleration turns out to be d square x by dt square plus d square y by dt square. And again, these are all functions of time. Okay. Okay. All right, so we've said this many times, but all we're saying is the following. If somebody asks you to describe a 3D motion, they're asking you for these three functions, and then you know how to calculate the velocity as a function of time. And you know how to calculate acceleration as a function of time. Okay. Okay. All right. All right, now, so we have the general statements. We know 3D motion. So now we can specialize to a special kind of 2D motion. Okay. So since we're talking about 2D motion, what we're doing is this thing is constant. It's not changing in time. Okay, that coordinate is not changing in time. So we're just talking about x, y coordinates. So if you throw a projectile and it's traveling in this plane, the z-axis is in that direction, and z is not changing. So it could be, you can take it 0. Okay. So again, in particular, we are interested in this projectile motion. Okay, so we're going to toss something, and the only force acting on it will be the force of gravity. Air resistance will be negligible, and so on. And the nice thing about that is acceleration is constant, and we know the direction of the acceleration. Okay, so that's the acceleration. When will acceleration be not constant? Well, if there was air resistance, but let's say air resistance is negligible, when would G not be constant? Sort of a trick question, but well, if you throw a ball, let's say 100 miles up in the air, so then G will change. But I guess we don't have to worry about you throwing a ball 100 miles up in the air. Okay, so. But if you get to shoot intercontinental ballistic missiles, then stuff is different. But then air resistance is not negligible. All right, let me show you a simulation, and I want you guys to try and notice some stuff. All right, so I'm going to shoot a projectile. Air resistance is negligible in this thing. You will, the simulation will show you the components of the velocity vector, the x and y components. Okay, and the x component is that, there's the y component. Okay. All right, so we'll redo that. Okay, initial velocity is, there was air resistance there. That's why it was not parabolic. Okay, so, all right. So what I want you to do is notice the components of the velocity, okay? So velocity vectors, components, no air drag, and let's fire. All right. What happened to the x component of the velocity?
Nothing,
Nothing. Why not?
because there's no force acting on it.
There you go. There was no force acting on it in that direction. Okay, so so in so for this axis, there's the acceleration, and it is 0I minus gj. The acceleration in the x direction was 0, and that's why the x component of the velocity didn't change. There was acceleration only in the y direction, and so the y component of the velocity was changing. Okay, this was non-zero. Vx was equal to v naught x plus ax times t. This guy was 0, so the x component of the velocity remained constant. Okay? All right. That's what this diagram is showing you. Okay? Okay. So you see, you fire, there's the initial speed, there's the launch angle, and the x component of the velocity is constant. So at the very top of its trajectory, all it has is x component of the velocity, and it's the y component of the velocity that's changing. The acceleration is pointing downwards and so on. Okay? And we'll show you in a second that this trajectory is a parabola. Okay? As a reminder, so again, this is y, x. What does this graph look like? What is this? I'm sorry? It's a parabola. Okay. If A is positive, the parabola would open upwards. If A is negative, the parabola will be opening downwards. Okay. All right. Okay, again, so air resistance is negligible. The horizontal and vertical motion are independent of each other, and the trajectory of such a projectile is a parabola. Okay. So again, so for this axis, acceleration is that, which is 0I minus gj. Okay. And so for instance, so if you look at the x component of the motion, x minus x naught equal to v naught x t plus 1/2 ax, acceleration in the x direction, t squared. This guy is 0, so that term is gone. We'll say that you're launching at the origin, so this term is 0. This guy is gone. V naught x, the initial x component of the velocity, is the initial speed times cosine of the launch angle times t. Okay. So there is the x position of this projectile after time t. So if at t equal to 3 seconds, there is the x coordinate. Okay, and that's what this formula is giving you. Okay. And there is the y coordinate. Okay, and let's find out the y coordinate. So we'll do the same thing. Y minus y naught equal to v naught y t plus 1/2 ay t squared. Again, this is 0. You start at the origin. Y equal to v naught y is v naught sine theta naught t, and ay is minus g. Okay, and so there is that guy. And then you can do the following simple trick. From here, solve for t. T is x divided by v naught cosine theta naught. And put that in here. Put that in here. And this is what you get. So what you get is that the y coordinate, if you throw a ball, the y coordinate at any given point is related to the x coordinate like that. Okay? Y is a quadratic function of the x coordinate. Okay? And that's a parabola. So that trajectory is a parabola. Okay. Again, under what assumption did we derive this? We derived it under this assumption. And this is saying the only force acting on it is the force of gravity. Okay? All right, but you knew all of that. Okay. All right, now what we'll do is we'll give you a range and maximum height formula. Okay, so here's what we're doing. We are going to launch a projectile. V naught is its initial velocity. Theta naught is its launch angle. And there's the range. So the range is the horizontal distance it traveled when it's come back to the same vertical position. Okay? So for instance, the range formula, if this was the initial position and this was the final position, you can't use the range formula because those vertical positions are not the same. Okay, the y coordinates are not the same. And this is the maximum height formula. Okay, so the range is the speed square times sine 2 theta naught. Theta naught is the launch angle. Okay? Divided by g. Okay. You guys all know this. When do you get the maximum range? At what launch angle do you get the maximum range?
45 degrees.
45 degrees. And here's where it's coming from. See, for a given launch speed, if you want the maximum range, this is fixed, this is fixed. The only thing that you can change that is this. And the maximum value this can have is 1. And that can happen for sine 90. So theta naught, launch angle is 45 degrees. Okay? All right. Here's the maximum height it would travel for this launch speed and this launch angle. Okay. Now, for a given launch speed, what should be the launch angle to get the maximum height? I mean, this is a very silly question. I'm sorry? All right, you got to shoot it straight up. And so sine 90 would be 1 and 1 square would be 1. Okay? Yeah. All right. Now, many people probably don't know this. Do you notice anything? So these are with negligible air resistance. And you see, for a 30-degree launch angle and a 60-degree launch angle, you get the same range. So it turns out that for complementary angles, you get the same range. Okay? Okay, so here's the trajectory with when the acceleration of the ball is given by this. Okay, when there are no other forces but gravity acting on it. Okay, but it turns out that if you give the ball a spin, other forces come into play and the trajectory changes from parabolic trajectory. So here's the kind of trajectory you'll have with the top spin. Okay, so this is what you do in tennis. Okay. Oh yeah, we have a tennis player. Yeah. So the more top spin you give, the more likely it is to fall inside the baseline, okay? You can hit it as hard as you want, but you give it enough top spin and it falls in, okay? All right. Yeah, so here's what's happening. So here's the ball going. I guess I can't stop the simulation. It starts off with the cylinder not spinning, and when the cylinder is not spinning, the airflow is even around both ends. Once the cylinder starts spinning, what happens is it drags air. This air is flowing faster than that air at the top. And you'll learn about Bernoulli's effect. Um, um, so here's, let's say, a tennis ball. It's spinning like that, and it's traveling in this direction. The air here is going faster than here because it's this air has to travel a larger distance. So velocity at the top, velocity at the bottom. Velocity at the bottom is greater than velocity at the top. And you will learn about a Bernoulli's equation 1/2. This is the rho is the density of air, velocity square plus plus rho GH. Plus pressure. Okay, what this equation is telling you is the pressure at a given location plus the kinetic energy of the air fluid flowing per unit volume plus the potential energy. The sum of these three terms are constant. Okay, right now we'll take these to be the same. So we'll apply this. Okay, so these three terms here and these three terms there are equal. Okay, so pressure at the top plus 1/2 rho velocity at the top square is equal to pressure at the bottom plus 1/2 rho v at the bottom square are equal to each other. That's what this equation is telling you, okay? Well, the velocity at the bottom is greater than the velocity at the top. So whenever a fluid flows faster, the pressure there is lower. The pressure at the bottom is lower, the pressure at the top is higher, so the ball gets pushed up. Okay? So that's what I want you to remember. Okay? Anytime a fluid flows faster, the pressure at that location is lower. Okay? That's how you get the planes to fly. Okay? So here's the cross section of an airfoil, and here's what you're trying to do. So the air there has to travel a faster distance. Velocity at the top is greater than velocity at the bottom. Pressure at the top is lower than pressure at the bottom. Okay? And so the lift, okay, you don't want the plane to fall off the air, do you? So the lift is equal to the weight of the plane, and the lift is pressure at the bottom minus pressure at the top times the area of the wing. Okay? All right. All right. Uniform circular motion. Okay, so Uniform refers to the fact that the speed is constant, the speed is not changing, and the trajectory is circular. Okay, so here you're driving in a circle. Is your velocity changing? Your speed is constant. Hmm? Yeah,
Velocity is changing.
I'm sorry?
Velocity is changing
Why is it changing?
because of the direction.
Right, so the direction is changing, okay? So when only the direction of the velocity changes, it turns out, well, anytime velocity changes, you're accelerating. And when only the direction changes, it turns out that the acceleration is perpendicular to the trajectory. Okay? All right, so if you're there, the acceleration is perpendicular to the trajectory, and if you're traveling in a circle, the acceleration is pointing towards the center of the circle. So what would you call it? What would be a good name to call
Centripetal.
it? There you go, centripetal acceleration. Okay? So that's, all right, so, and the magnitude of the centripetal acceleration is your speed square divided by the radius. Okay. Okay, this slide goes through the proof of it. What it's showing you is the direction of the acceleration is toward the center, okay? And the magnitude of the acceleration is speed squared divided by r. Okay, so that's what it's going through, okay? So it's showing you the acceleration is pointing towards the center. Okay? Centripetal acceleration is also called the radial acceleration because it's in a radial direction. Okay? Actually, negative of the radial direction, but it's in a radial direction. Okay, so what are these terms? Tangential and radial acceleration. What does this mean, tangential acceleration?
It only intersects at one point.
I'm sorry?
It only intersects at one point.
Okay. No, it's tangent to the trajectory. Okay. Radial acceleration is pointing towards the center. Okay. You have tangential acceleration when speed changes. Okay. That is when the magnitude of the velocity changes. Okay. And you have radial acceleration when the direction changes. Okay, and of course, if you have both speed and direction changing, then you have both accelerations. Okay. So, for instance, let's say here's a curved road, and if you were driving at constant speed, then this tangential acceleration would be 0. Okay. Again, you see why you call it tangential acceleration, because it's tangent to the path. Okay. So if your speed were not changing, then that would be 0. And when would you have a radial acceleration? Whenever the road curves. Would you have radial acceleration when you're driving on a straightaway? No, because then the direction is not changing. The only thing you could have is tangential acceleration, okay, if your speed was changing. All right, so those are the two accelerations. Yeah. Do you guys understand that? All right. All right. Let's say you're a pilot and you're flying in a plane that travels at 200 miles per hour through air. Let's say the wind is blowing at 50 miles an hour east, so west to east, so it's a 50 mile an hour west easterly wind, I guess that's the terminology used. Okay. You want to head north, which way would you fly? Yeah, so you'd have to fly this direction. And what particular direction would you have to fly? So you would have to fly this would be a velocity through the air, and this would be the velocity of the air. So these two vectors should add up to give you a northerly velocity. Okay. All right. And if the wind speed changes, then you have to change the direction in which you're flying. Okay. So we want to be able to answer questions like this. Okay. So let's build the technology for that. You guys understand? All right. So here's the deal. Okay, so we will use, this is a reference frame, and here's another reference frame. Okay? And this reference frame will be moving with constant velocity. Okay, that's what we'll do. So for instance, okay, here's a real life situation. Okay, so let's say in this car, somebody is juggling inside this car. Our question will be, what does this person see and what does this person see? Okay, so that's the kind of step. All right, so here's one reference frame. Here's another reference frame. Okay. So let's say something happened here. So here's a ball toss in the air. The position vector this person sees is that. The position vector this person sees is that. Okay. And the two position vectors are related like so. Okay, so here's a particle. The position as seen in the A frame is, the position vector as seen in the A frame is, the position vector of the particle P as seen in the A frame is equal to the position of particle P as seen in the B frame plus this plus that. What is this? That's the position of the origin of the B frame with respect to the A frame. Okay. All right, so position in A frame is position in B frame plus the position of B frame with respect to A frame. Okay. The way to remember this is the following. This is particle in A frame, and we're just introducing a B in between. Particle in B frame plus. Okay. All right. So if this is B flying in there, how does this guy describe the motion of the B? By giving you this. And how fast is that frame moving? And this guy is describing the motion of the B like that. Okay. And now once you have these guys, you can calculate everything that you want to calculate. Okay. You are great at taking derivatives, and just start taking derivatives. Okay. Okay, so this would be the velocity in frame A, velocity in frame A. This would be the velocity in frame B, and this is the velocity of frame B with respect to A. Okay. All right, so I'm going to ask you a question in a second. Think about it before you shoot. All right, let's say this frame is moving at constant velocity, so it's not accelerating. So we'll take a second derivative and say, let's say that's 0. So what it's saying is the acceleration in frame A is the same as acceleration in frame B. Okay. All right, here's the question now. So let's say this is frame B and this is frame A. Inside this frame, let's say you're tossing a ball. What is the trajectory of that ball? Let's say you're traveling in a train, which is traveling at constant velocity. You toss a ball. It will be parabolic. This guy, this person will also see a parabola. Okay. What will be different is, so I'm traveling, so let's say, this is easier for you to imagine. Let's say I'm on a skateboard, I'm traveling at constant velocity, I'm tossing a ball, it's parabolic. What are you seeing? A wider parabola. Okay? The width of the parabola changes. And that's what this statement is. See, the acceleration is the same. The acceleration is both see acceleration due to gravity, and they both see the same trajectory. Okay? All right, so this is the most important formula that we'll be using. Okay? So velocity with reference to frame A is velocity with reference to frame B plus velocity of frame B with respect to frame A. Okay? All right, so here we'll apply this to an example. Okay, so for instance, let's say it's raining, and it's raining straight down, and you're driving in this car. What do you see? How do you see the rain falling in the car? I'm sorry? Well, okay, so if you were standing on the ground, you see the rain falling straight down. Now you get in your car and travel in this direction. Do you see the rain falling straight down? Okay, so you see it like this. This is what you'll see. Okay, and so let's see. We'll show this to you. So velocity of rain with respect to the car is equal to velocity of the rain with respect to ground, which is straight down, plus velocity of ground with respect to the car. Okay. Well, what is the velocity of the ground with respect to the car? When the car is moving in this direction, velocity of the ground is in that direction. Okay. So this would be velocity of rain with respect to ground minus velocity of car with respect to the ground. Okay. So velocity of rain with respect to ground minus the velocity of the car. That's the direction of the rain. Okay. All right. So anyway, we will be using that formula, and you'll see a couple of problems. So we'll be adding velocities. Okay. So for instance, going back to the example of the plane, this is the velocity of the plane with respect to air. This is the velocity of air with respect to ground. And so velocity of the plane with respect to the ground is velocity of plane with respect to air plus velocity of air with respect to the ground. Okay. This vector plus that vector is velocity of plane with respect to the ground. Okay. All right, guys. So that finishes this chapter.